Welcome to the Explainer. Today, we're going to put on our detective hats to solve a classic linear algebra puzzle. We've got transformations, we've got matrices, and right in the middle of it all, there's a single unknown variable holding all the secrets.
So here's the central question you got to ask, right? How can one tiny, simple rule, an inequality about the outcome of a transformation, tell us something so specific about its hidden parts? Well, that's exactly what we're here to find out. Our mission is to follow this one single thread of logic all the way to the answer.
All right, let's get into it and examine the evidence. We're dealing with two linear transformations, S and T. You can just think of them as operations that stretch, squash, or maybe rotate vectors in space. We have the matrices that define them, and here's the catch, there's a crucial variable missing. So here's our evidence file. This is what we have to work with. We've got the matrix for the combined transformation ST. That's just what happens when you apply T and then S. And we have the matrix for S all by itself. And notice, our prime suspect, the variable A, is just lurking there in plain sight, inside both of them.
Now this right here is the smoking gun. This inequality might look super abstract, but trust me, it's telling us something very, very concrete. Think of the image as the output space. It's the shape you get after the transformation is all done. And this clue is telling us that the final shape from the combined ST transformation is, well, flatter. It has a lower dimension than the shape you'd get from just using S. It's kind of like squashing a 3D object down into a 2D drawing. And that is the thread we are going to.
So, what does this clue actually tell us in practical terms? It's time to follow the chain of logic, step by step, and see exactly where it leads us.
First things first. Our clue directly implies that the combined ST transformation is not an isomorphism. Now, that's a fancy term, but all it really means is that it's a one-way street. It's lossy. It squishes our vector space down into a lower dimension, and when that happens, some information is just lost forever. You can't perfectly reverse the process.
And that leads us directly to our next deduction. If you can't perfectly reverse a transformation, then its matrix just can't be inverted. There's literally no undo button, mathematically speaking.
So, what's the big deal? Well, this whole chain of logic brings us to one of the most powerful tools in our linear algebra detective kit, the determinant. You see, a square matrix is only invertible if and only if its determinant is not 0.
And there it is. That's the breakthrough. Since we know our matrix for ST is not invertible, its determinant must be equal to 0. We've done it. We've translated our abstract clue about dimensions into a concrete equation that we can actually solve.
Okay, so now we have our weapon, the determinant, and it is time to use it. By setting the determinant of matrix ST to 0, we can finally figure out which values of A could be responsible. Let's go unmask our suspects. So, we take the determinant of matrix ST, and we set it to 0. When you expand it all out, and don't worry, we'll spare you the gritty details, it simplifies beautifully into this very clean quadratic equation, a squared minus a equals 0. And solving that is pretty straightforward. It gives us two possible values for a, our two main suspects in this case, a equals 0 and a equals 1. But the big question is, which one is the true culprit? We can't just stop here. One of these values might be an imposter trying to lead us down the wrong path. We have to test each suspect against our original critical clue, that inequality, to see which one actually holds up under scrutiny. First up for interrogation, suspect number 1, the case where a is equal to 0. Let's see if its story checks out.
So we plug A equals 0 into both of the matrices. Now we calculate their rank, which, remember, is just the technical term for the dimension of that output space we talked about earlier. And look at this. For both ST and S, the rank is 2.
Uh-oh. This is a direct contradiction of our key clue. Our condition was that the dimension of ST's image had to be strictly less than the dimension for S. Well, 2 is not less than 2. So, A equals 0 is not our answer. It's been cleared of all charges.
That leaves us with our second and final suspect. Let's see if the case against A equals 1 holds up any better.
All right, let's try our other suspect. A is equal to 1. We plug it in, and we calculate the ranks all over again. The rank of the ST matrix is 2, but the rank of the S matrix is 3.
And there we have it. The condition is met. 2 is less than 3. Our original clue holds true. We've confirmed our suspect. The only possible value for A is 1.
So, with the mystery of A now solved, we're not quite done. We can use this information to complete the final part of the puzzle, finding the matrix that represents the transformation T.
You know, the beauty of matrix algebra is that it gives us a clear path to isolate an unknown. We know that the matrix for ST is S times T. So to find T, we just need to undo S. And we can do that by multiplying ST on the left by the inverse of S.
After finding the inverse of our now known matrix S and performing the multiplication, we get the final answer. This right here is the matrix for the linear transformation T. And with that, case closed. So the key takeaway here is really how a single abstract clue, an inequality about dimensions, can trigger this cascade of deductions that solves a very concrete problem. We went from dimension to invertibility to the determinant and finally to our answer. It just shows how interconnected all these concepts are. But you know, solving one mystery just opens another. Looking at this matrix for T, what does it actually do? What kind of geometric twists and stretches does it perform on the universe of vectors it touches? That sounds like a case for another time.